All right. Um, so I got to explain the rumbling noise in the background. Some of you know this already. They're redoing the roof on my home right now. And so there's kind of a low rumbling noise. They're removing my old roof, and hopefully, I think it's a little too early for us to hear pounding as they apply the new roof. But anyway, strange noises. It's my house that's responsible for the strange noises. Okay, I've got 3 problems that students have already requested, so I'm going to start sharing here. And then we can dig in. So hopefully everyone's seeing my screen right now. And there's the number 37 up there. Okay, number 37 was the first one requested. This is from the chain rule lesson we had last time. So the directions are: find an equation of the tangent line to the graph at the point 2 comma f of 2. Now, you'll notice up in the corner I don't have 2 comma f of 2. Do you see what I did up here? Let me see if we can get this pen going here. You see how I have the point 2, 3? So I plugged 2 into the equation for x. 2 squared is 4, 4 times 2 is 16, 16 minus 7 is 9, and principal square root of 9 is 3. So in place of f of 2, I put 3 up there. Okay. So the plan of attack here is, first find the general derivative, then find the specific derivative at x equals 2, and then go ahead and find the equation using that point up in the top right corner. So the first thing I did is let's try that again. I rewrote the function using the 1/2 power notation, and then I found the derivative in this line. So we use the power rule. 1/2 comes down in front. Keep the quantity. Reduce the power by 1. We have a chain rule here because we have an inner function, so also multiply by 8x. Simplifying it and putting it back into algebra notation, I put the 4x squared minus 7 under a square root sign on the bottom. Why? Square root because of the 1/2, on the bottom because of the negative. 1/2 times 8x is 4x, so there's my general derivative. Now, what's the derivative at 2? So we find out by substituting. Pretty easy again. On the bottom, 2 squared is 4. 4 times 4 is 16. 16 minus 7 is 9. Root of 9 is 3. And on top we have 8, so it's 8/3. And then the rest of it is the old mx plus b situation. Plug in your slope in for m. And then substitute in your point, which, if you remember from the top, was 2 comma 3. So I plugged in 3 here. I didn't show it, but 8/3 times 2 is 16/3. Anyway, subtract, you get negative 7/3. So here it is. Final result. What's the equation of the line tangent to the curve at the point 2, f of 2? This should be it. So that's number 37. So I think that was Maki. Maki, if you have any follow-up question to that, let me know. Okay. If not, I'm going to go to your second question, which was to do a problem like number 53. So I figure let's do 53. So from the previous assignment, number 53. And pretty simple, it just says find the derivative. Okay. So now I have a couple options here. I could just hammer that thing out and then just do a regular old power rule derivative. But I decided, since we still need practice on the power rule, I mean on the product rule, that I would go ahead and use the product rule. So here's my product rule. The first times the derivative of the second. Okay, derivative of the second. Power rule, right? 3 comes down, reduce the power by 1, and then there's the chain rule, plus the second times the derivative of the first. Okay, so that's basically the derivative, except of course we have to expand that. So here I expanded 3x minus 9 squared. I mean, if you have to do that separately, it's 3x minus 9 times 3x minus 9. And where did I get the 9x from? That's the x times 3 on the end. X times 3. So when I'm all done with this, I got to multiply this by 9x again, and that's what I did right here. Okay. And then on the second part, you've got what? You've got this 3x, and I don't know what to tell you, except that has to be hammered out. 3x minus 9 times 3x minus 9 times 3x minus 9. I'm not going to go through that now, but that has to be done. Do you need to graph which ones, Maki? You mean back? Are you talking back on 37? Oh, all right, Maki. Yeah, all right, so I'm going to just interrupt this for a second. Follow-up question number 37. The directions did say use a graphing utility to check your answer. So it doesn't really affect your answer, but you can pull out Desmos and just see, is that equation came up really the tangent line that just barely touches the graph at one point, at the point 2, 3, and visually check it. That's the only part of the the only part. So the graphing doesn't really help you answer. It's just a checking device. Okay, to finish up 53 here. So here's the first part of the product rule. Here's the second part, and then you still have a combination of the two. And when I did that, there's what I came up with. So just a lot of algebraic coursing around, but most of the line up here is that derivative line right up there on the on the top. Okay. That's 53, and then I was asked about number 61. So I'm going to go to number 61 next. Number 61. What do we have for directions here? Find the nothing special. Find the derivative. Okay. So here's the way it's stated in the beginning, right out of the book. I rewrote it using fractional exponents instead of the roots. And then, okay, execute the derivative. So for the first term, we can start with the power rule. 1/2 comes down, keep the quantity, reduce the power by 1. So 1/2 goes to negative 1/2. And then, of course, in blue, we have a chain rule. All right, now do the second term. We have 1/2 multiplied by a negative 1 gives us negative 1/2. Keep the quantity, reduce the power by 1, another chain rule. So, sorry, this is kind of mixed up because I got all these different colors in here. But what's 1/2? I mean, the 2x is on the top, and this 2 is on the bottom because of the 1/2 from up there. And of course, the 2's are going to cancel, right? You know what? I'll tell you what. I think I'm going to, let me just redo the part from there on down. Okay? So it's a little too messy. So give me a second here. I'm going to clear out. Okay, so now let's just start from where we were there. We've got our derivative. So when you write that, we know that this is going to be what? A root on the bottom. So let's put that down. Then we've got the 1/2, like this, and then we got a 2x. On this side, after the minus sign, again, we have a root, but it's a little different, isn't it? It's x squared minus 1. And we've got a 1/2, and we've got a 2x again. So, you know, we certainly can do this kind of cancellation. These 2's are gone. So what we've got now, simplified a little bit, is this. Now I'm going to get rid of my keyboard so I can write a little bit better. And then on the other side, that's supposed to be an X on the top. Sorry about that. So about the only thing, I mean, should we get a common denominator? I don't know. You could. I don't know if it's worth it, but this is good. And then if you did get a common denominator, what? You'd have to multiply this one top and bottom by x squared minus 1, and this one top and bottom by square root of x squared plus 1. And then you would have what? Anyway, that would get you on the road to the final. I don't know if we need to go any further, but they didn't ask us to find any. Yeah, that's it. So there are different forms of this. I don't know if it's worth it to do any more right now. Okay, that's 61. Those are the 3 I was requested. Are there any others from the chain rule lesson? Don't forget, you guys, you can just speak up. Any other chain rule lesson 2.5 questions? So I had somebody come into my office because they were going to be gone for this lesson and asked me to kind of give them a little preview. And it's kind of refreshing, but I really don't have a whole lot of new. So this is going to be, I don't have any new procedures to tell you today. Rather, we're just going to kind of, we're going to just maybe do a few derivatives multiple times today. So I guess kind of refreshing. No real new skills today, just the idea that you can take a first derivative, a second derivative, a third derivative. Let me get to the title here. And so this lesson is simply called higher order derivative. Now, I believe you've seen this notation already, right? Where we use an apostrophe. So this f double prime of x means find the second derivative. There are other notations for that. Let me just show you the next slide. Maybe we'll come back here. Yeah, this f prime notation. That's one of the discoverers of calculus, Isaac Newton, used that notation. So on the left you see a first derivative, f prime of x. Here you see second derivative, f double prime of x. Leibniz, the German, who was a co-discoverer of calculus, he used this notation over here. So this refers to the derivative of the function with respect to x. This is how Leibniz did a second derivative. The second derivative with respect to x. So just so you know, you may see a little bit of both of those notations as we move forward. So now, as I go back to this slide where we were before, these are the two we just talked about. Well, what about this one? Well, the problem is once you get like the 6th or 7th derivative, it looks like a picket fence when you have all these primes. So after, I don't know, sometimes you'll just see a little number in parentheses like you see on the left here. So this means the second derivative. So anyway, we gotta get over that because you're going to see a little bit of both, I think, in the assignment. Okay, so notation. Functionally, here's some things I need you to think about what derivatives do. Now, you should already know this, that when you find the first derivative of a function, what does it give you? It gives you this instantaneous slope. Sorry, nose blow coming up here. Okay, so we have first derivative is an instantaneous slope. And I talked about second derivative when it comes to distance being what? The first derivative was velocity, second derivative was acceleration, but I didn't talk to you when it comes to graphing. So this is more of a graph, you know, these are what? I don't know, should I just call it graph results over here on the right? So when you take a first derivative, it tells you how steep the curve is at that point, positive or negative and all that. When you take a second derivative, you get what's called concavity. Concavity means, you know, if the curve looks something like this, if it's cupped up, we call that concave up, and that happens when the second derivative is positive. When the second derivative is negative, you get, maybe should have said smiley face. When you get the second derivative is negative, then you get sad face, you know, concave down we call that. And if the second derivative is 0, then it's what we call an inflection point. It's like changing from concave down to concave up or concave up to concave down. Here, I'll show you. If we take a cubic graph, it looks like, generally, here's what a cubic graph looks like. Right? You guys should all recognize y equals x cubed. Well, let me change colors here. In this section of the graph, we agree the graph is concave down. In this section of the graph, it's concave up. And right here, at this one point where it's changing from concave down to concave up, that's an inflection point. Here, it's written more completely over here. That's called an inflection point. So, the second derivative tells you something about how the graph looks. And so you can go attack a totally strange function, and this concavity tells you more about how the graph is shaped, becomes a graphing tool for you. So that's new to you. Yeah. So here, this is just you know, I forgot I even had this slide here. I drew it real nice and pretty for you. Let me make this bigger so we'll take more advantage of the screen here. So the first derivative gives you the instantaneous slope, and you already know a positive slope means, you know, going uphill from left to right, and a negative, you already know what that means. And then here's what I was just talking to you about. When you take a second derivative, it gives you what we call the concavity of the graph. A positive means it's concave up. A negative, it's concave down. And then there's that special thing we talked about. When it's 0, it's an inflection point. And then here's the example, only not more nicely done, that I was talking about on the previous page. Here's a y equals x cubed. You can see it's concave down here. It's got that frowny face shape. Over here, it's concave up. And right at that one point right there, we call that, That's like a changeover from one concavity to the other. We call that an inflection point. So right here, the second derivative will be 0. The second derivative over to the left here will be negative because that's concave down. And the second derivative to the right here, that's going to be positive, resulting in a concave up curve. So one thing multiple derivatives give you is they give you this, now we've learned this new thing called cavity that tells us something new about the graph. So here we go back to some past things we did. If you're working with physics or any kind of science where you have distance, we know that that's usually the original function, distance. And then when you take the first derivative, it's velocity, second derivative acceleration, and third derivative jerk. So that's a review. By the way, here's the alternate way to write the third derivative down here. You see what I mean? This is starting to get to be like a picket fence here. It almost looks like s to the 111 power, and of course it's not. And so to avoid that confusion, this way down here is actually clearer. So I've got an example up on the slide here. If this were your distance function, and just a reminder that negative 16t squared, that's gravity's effect pulling an object back down to the earth. If you take the first derivative, this is the velocity. So yeah, we got them up on the top here. Distance, velocity, acceleration, and in this case, what's the third derivative? What happens when you take the derivative of negative 32? It's 0. So whatever, in this case, there is no jerk. And by the way, in an object that's just thrown, that's not interrupted by a bat or a kick or anything else, just follows the natural gravity approach, there won't ever be any jerk. It's only when, you have a collision or something like that that we have problems with that. Okay, let's dig in and do a problem. So this is number 7, and it's on the 2-6 assignment. Find the second derivative, it says. Okay. The function is 3 over 4t squared. So I start with the first derivative, and because it's a quotient. By the way, I could have wimped out here, and I could have done what? I could have called this 3/4 times t to the negative 2, and then I could have done the power rule. But again, for practice, on the quotient rule, I did the quotient rule. So we have denominator times derivative of numerator minus numerator times derivative of denominator, all over denominator squared. 4t squared minus 24t. This is nothing, right? This wipes out, and I get negative 24t over 16t to the fourth. And if I just simplify my fraction a little bit, there's my first derivative. Okay, we were supposed to find the second derivative. So here we go with the second derivative. Again, I use the quotient rule, denominator times derivative of numerator. Again, that's going to be gone, right? Because it's times 0, minus numerator times derivative of denominator, all over denominator squared. Okay, well, when you have a minus and minus a negative 18t squared, that's going to be plus 18t squared. And then just simplify it. There's my I'm not sure. Oh, this is the other way to do it. Yeah. So anyway, there's my second derivative. What this is down here, what if I had just called this in the beginning 3 times 4t to the negative, I'm sorry, 3/4 times t, you know, this is also 3/4 t to the -2. And then I could have just done the power rule, and all I'm showing is you come up with the same answer. You know, yes, this is in a little different form, but these two are exactly the same. Okay, so there's just a second derivative. That's nothing new. We knew how to do that before. All right, how about number 16 says find the third derivative. All right, so, well, this is an easy one. Why? Because, well, we don't, I mean, it's just a good old power rule, right? So the first derivative, 4x cubed minus 6x squared. Okay, well, now let's do the second derivative. Power rule again, 12x squared minus 12x. Third derivative, power rule again, 24x minus 12. Nothing very complicated there. Okay, so again, this is kind of light today. Let's go 18. Third derivative again? Yeah, let's do this one. Derivative. Okay, here's our function. What did I do? Well, I took, all right, instead of squaring it, I took the, you know, the more manly approach here. I used the power rule, but then I guess you could say I also used the chain rule. Bring the 2 down, reduce the power by 1, and then don't forget about the chain rule. Now in this case, what is the derivative of x minus 1? It's 1. So that's why I didn't have it up on the screen before, but it's good to think of it being there. And then I just multiplied the distributive property out. Okay, we got our first derivative. So what's the second derivative? Power rule, 2. So what's the third derivative? And what happens when you take the derivative of a constant? It's 0. All right. Let's take a look at a different example. This time we're going to go to 24. And if you look, if you got your book handy, the directions this time say find whatever it asks you for. So like on number 24, they gave you the function, the square root of 2t plus 3, and then they said find f triple prime of 1/2. So in other words, we find first the third derivative in general, and then find the third derivative at 1/2. So first we got to find the third derivative. So I rewrote the function as 2t plus 3 to the 1/2 power. I did the power rule. 1/2 comes down, leave the expression, lower the power by 1, and then, of course, very important, chain rule, right? Now, can we simplify this answer a little bit? Sure. What's 1/2 times 2? That becomes 1. So can't I just write it this way then? You know, because 1/2 times 2 is 1, I really can just write it as 2t plus 3 to the negative 1/2. Okay, first derivative. Second derivative. Power rule again. Bring negative 1/2 down. Keep the expression. Lower the power by 1, so lower it by 2/2. Chain rule, 2. Again, what's negative 1/2 times 2? This time it's negative 1. So this time you notice I do have a negative sign out there. And now we got to do the derivative one more time, right? Okay, so the third derivative. Negative 3/2 times negative 1 is positive 3/2. Keep the expression, lower the power by 1. It's getting lower. Now it's at negative 5/2. Chain rule, 2. Can you simplify 3/2 times 2? Sure, that's 3. So there's my third derivative simplified. We're almost done. Now we've got the general third derivative. What's the third derivative at 1/2? So now we just plug in 1/2 for t. What's 1/2 times 2? 1. What's 1 plus 3? 4. Now the question is, I'm going to just write this on the side. I mean, you got the 3 out here. And now we've got that down to 4 to the negative 5/2 power. Well, isn't that the same as 3 over 4 to the positive 5/2 power? How do you take something to the 4/2 power? I'm sorry, the 5/2 power. Well, the bottom is root, the top is power. Do the root first. What's the square root of 4? 2. And then what's 2 to the 5th power? 2 times 2 times 2 times 2 times 2 is 32. So, you know, so that's where I got that result from. All right. Let's do another. Let's do number 38. So 38 from the assignment. Directions: find the second derivative and solve the equation, the second derivative of x equals 0. So in other words, this one, after I find the second derivative, I have to set it equal to 0 and solve. So, find the second derivative. So first I rewrote it. This we have to use the product rule on, right? Because there's no way to combine this x with stuff that you're taking the square root of. Okay, so we have a product rule. First derivative. The first times the derivative of the second. The second I use the power rule on. You know, bring the 1/2 down, keep the expression, lower the power by 1, chain rule. The derivative of 4 minus squared would be negative 2x. Okay. Can I simplify? Sure. What's 1/2 times 2? What's 1/2 times negative 2? It would be negative 1, right? And then we've got negative 1 times x times x. So in other words, it's negative x squared, right? Okay. I mean, that's down here, negative x squared. But we got to do the second half of the product rule. The first times the derivative of the second plus the second times the derivative of the first. Easy derivative of the first. So let me just show you where we are now. So yeah, here comes the pounding now. Sorry guys, it's going to get a little loud. So anyway, here's the first part of the product rule. Here's the second in black, right over here. So all I did was rewrite it. And then, okay, you can see I went and got in blue, I went ahead and got a common denominator, brought them together. Get rid of that crazy thing. If I can find it. Sorry, I'm going to just get rid of this thing. It's in the way now. There we go. Okay. So the bottom line is here's how the first derivative comes out. And now you've got to execute that derivative again, right? Because the directions of the problem were find the second derivative. Again, I don't want to go through the details right now, but I have to do the product rule again because I have part 1 times part 2. So once again, I execute the product rule. The first times the derivative of the second plus the second times the derivative. So here's the first times the derivative of the second. And here's the second times the derivative of the first. Put that all together, and here's what it comes out to. And now I got to remember, oh, that's right, I was supposed to set the second derivative equal to 0 and solve. Okay, so one more step. This is easy compared to the rest, and that is I need to solve. I can multiply both sides by the square root of 4 minus x squared cubed. And that's goodbye denominator, and it'll be 0 on the right. We have this left. It's real easy to factor. Set each factor equal to 0. Solve. Okay. Now, when is the second derivative equal to 0? Okay, I got to just think this through here. Why did I cross those out? Plus or minus the square root of 6. Hang on a second. I can't remember why. Why did I? Okay, I did the algebra right. We've got, and you remember, you're finding out when the second derivative is 0. So really, what you're finding is inflection points. Remember that? When the second derivative is 0, you've got an inflection point. Not seeing in my head. Why did I mean, I did the algebra right. Oh, I see why. Because if you go back to the original, if x is 6, you've got a negative under the square root sign. Do you see that? So just go back here. What did I find? No, I said square root of 6, right? But what happens when you square the square root of 6? Right here. The square of the square root of 6 is 6, and 4 minus 6 is negative 2, and you can't take the square root of negative 2. So that's why I crossed out that part, because it creates an impossible calculation of the original function. Now, just to confirm things, here's the graph of that function. Are we right? Yep, right at x equals 0, right there. Notice we are at an inflection point because the graph changes from concave up to concave down. And right at that change, yep, there is only one inflection point, so our conclusion was, I mean, we obviously did it right. Yeah, final answer is, where is the second derivative equal to 0? Only one place, at x equals 0. Okay, that's it for my, as you can tell, this isn't a lot new, just a couple new terms. Some more practice with derivatives. First time we've spent time with higher derivatives, past 2. I'm going to go to the assignment, but I want to see if you have some questions. So let me know, either speak up or put something in the chat window, or send me a text message, or call me. I should have a live cam on the roof so we could see what's going on up there. I'm really happy because my roof has been compromised for about a month now. Shingles flopping up there, and finally, in the next few days, God willing, I'll have that taken care of. Well, I'm going to show you the assignment. It's one of those every other odd configurations. This time, 45 will be your last one. Questions? So we're done a little bit early today. You can, of course, send me questions anytime you want. I'm not hearing any, so I'm going to stop the broadcast. Thank you, everyone. I'll see you tomorrow. Have a good day.